Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. I am pursuing my PhD in organic chemistry, synthetic organic chemistry from ISER Padhampur. So I am the TA of this course Retrosynthesis in Organic Chemistry, instructed by Professor Shramik Nanda from IIT Kharagpur. So here in these classes I discuss some name reactions and also some reaction by which you can form those different type of simple and complex molecule, which may help you to get an idea how to plan a retrosynthesis of any compound. So in the previous 3 classes I have discussed a similar type of question with some name reactions and some basic reactions to form carbon-carbon bond. So here today I will discuss basically 2 topics. We know about oxidation and reduction, so I will discuss some unique oxidation reactions and reductions reactions. I have tried to include most of the important name reactions based on this oxidation reaction. Whichever will be left, I will try to complete in the next week. Okay, let's start then. So today I will discuss different type of oxidation reactions. First we will discuss chemo oxidation, followed by Swan oxidation, then some concepts of zones oxidation and oxidation using PCC as a reagent, and also pyroligent oxidation. So first let's talk about chemo oxidation. So what is chemo oxidation? The chemo oxidation is an oxidation reaction used to synthesize aldehydes and ketones for the oxidation of primary and secondary alcohol. So it was named for the American chemist and Nobel laureate Professor Code and the Korean American chemist Professor Kim. So here you can see I have shown in the in general schematic diagram. If you take a alcohol and add N-chlorosuccinamide, NCS means N-chlorosuccinamide. You know the structure of succinamide. This is succinamide. This is the normal succinamide, and it is N-chloro. So the N contains a chlorine group. This is called N-chlorosuccinamide. Okay. If you add N-chlorosuccinamide and dimethyl sulfate and ED3N as a base, you will get ketone from the alcohol. So it has some limitations like the chemo oxidation process, but if it has some advantages like you can perform the reaction at a higher temperature than that of other oxidation reaction. But the drawback is if you take any there is an issue with the applicability of the reaction, because if your substrate is not susceptible to chlorination, that won't react under this condition. So if we go to see what is the mechanism behind this reaction, you can see first this dimethyl sulfate attacks to this fluorine atom and opens up this NCl and breaks this NCl bond, followed by this N- attack again to the sulfur and remove the chlorine from the system and form this intermediate. This intermediate reacts with our alcohol and forms this oxygen sulfur complex, and after that, by the means of addition of base, it will abstract the proton, followed by this way it will form this sulfone kind of complex, and after that removal of this from the system, we will get ketone as our product. So it has some limitation, like if by this process you can only oxidize primary alcohol and secondary alcohol, because if you take any allylic or benzylic alcohol like this, allylic or benzylic alcohol, what will happen? As NCS is a good chlorine source, as NCS also acts as a good chlorine source for the chlorination reaction, what will happen? As this type of substrate, due to this conjugation, has a this position is highly electrophilic. This position is highly electrophilic and resonance stabilized, so it will undergo it may undergo a SN1 type of reaction, and this because of that it will get removed and form this chlorine substituted product. It may form this chlorine substituted product. So to control that, there should be a very quick addition of this ET3N. If there is a huge time gap between this addition of this ET3N and this formation of this intermediate, this chlorine can reverse this by attacking at this position. To stop that, we have to add ET3N as quickly as possible. Okay, so it can also can be used as a good chlorination layer, by removing the use of ET3N. We can use this for different type of chlorination reaction. So what will happen? As we have already discussed, we just discussed about the Corey-Kim oxidation. So obviously, and they have given the reagent DMS. DMS means dimethyl sulfide, NCS and ET3N. So what will happen? Alcohol will be oxidized to aldehyde or ketone. So you have to find the alcohol centers. There is alcohol and there is another alcohol. Now see, it will just oxidize primary and secondary alcohol. So this one is attached to 2 carbon. So this is secondary. This is secondary. But here this OH is attached to 3 carbon. So this one is tertiary. So this one is tertiary. So we know that Corey-Kim oxidation reaction can only perform on primary and secondary. So this OH will be unreacted. Only which one will react? This one will react. So if we just try to draw the product, what will happen? This center will be oxidized and rest of the system will be intact. Rest of the system will be totally unaffected, and this OH will be also unaffected because it is tertiary in nature. Okay, so co-Kim oxidation reaction can be only applied for primary and secondary. For primary, it will transfer alcohol to aldehyde. For secondary, it will transform alcohol to ketone. And that if this reaction should not be applied for allylic alcohol and benzylic alcohol, because what is the drawback? Because in that case there is a probability of getting a mixture of product along with our alcohol, along with our carbonyl compound. We may get a chlorine substituted product. So next we will discuss about Swan oxidation. The Swan oxidation is an organic chemical reaction that is used to oxidize primary and secondary alcohol into aldehyde and ketone. The reagent is used in this reaction are oxalyl chloride, dimethyl sulfoxide, and organic base like triethylamine. So what is the advantage? The primary advantage of using Swan oxidation over Jones oxidation. Jones oxidation we will discuss after this. By this oxidation process you can oxidize a primary alcohol just to aldehyde. There is no question of over oxidation in this case. So if you want to get a simply aldehyde from alcohol without getting any over oxidized product to acid, you should choose this Swan oxidation process, because in this case there is no question of chlorination also. This is one very important one. So this is the mechanism. So what is happening here? First, this the dimethyl sulfoxide oxygen will attack to this oxalyl chloride and remove one of the chlorine atom from the system, forming this intermediate 3. After that, the removed chlorine atom will attack again to the sulfur and removing this oxalyl from system as a CO2 and carbon monoxide. How CO2 is this is going here, so this portion is eliminating as a CO2, this portion is eliminating as a CO, and another Cl minus. So what is happening? Then this intermediate 4 will react with our alcohol, forming this intermediate 6. After that, similar to the co-Kim oxidation reaction, base will eliminate this proton, base will eliminate this proton, and but here the advantage is there is no question of over oxidation, and next is Jones oxidation and PCC oxidation. First we will just trying to discuss all these type of oxidation reactions, because if you try to solve the question, that will be very easy for you, because I am just discuss the theory, then if I along with that, if we discuss some question, then we will get an idea that for which reaction which oxidation will be applied. But once you will learn what every type of oxidation and its limitations and advantage, then you can, by just seeing a reaction, you can think about that which oxidation type can be applied for those reactions. So first is Jones oxidation. Jones oxidation is the simple one, where the chromium oxide is used to oxidize alcohol, but the advantage of this reaction is the alcohol, if this is primary alcohol directly oxidized to undergoes over oxidation, forming this carboxylic acid. What happens? Actually this undergoes an aldehyde, and due to presence of this chromic oxide still in the system, it will again undergoes the oxidation, forming this carboxylic acid. Whereas this secondary alcohol undergoes oxidation to form a ketone. As there is no chance question of over oxidation, so that's why you just get a ketone. But in case of PCC oxidation, what is the advantage from this Jones oxidation? Thus in case of PCC oxidation, you will just get a aldehyde from the alcohol. So there is a one-step oxidation. There is a one-step oxidation in case of and secondary alcohol undergoes oxidation to give ketone. So now you know that primary oxygen gives aldehyde and secondary oxygen gives ketone. But here in this case, what will happen? what will be the product? Because here see, this alcohol is tertiary. So from first instance, you will think, okay, this will not react because tertiary alcohols do not undergo oxidation with PCC. But I will tell that. So just I just give 1 minute just to think about what will happen. So in this case, a different as this is a allylic alcohol. As this is a allylic alcohol, what happens in this case? For allylic alcohol, there is a special criteria for PCC, just for PCC. The PCC reagent is this one, pyridinium chlorochromate. What will happen? This oxygen will attack to this bromine. After that, this forming this rearranged product. Then again it goes oxidation. This as our product. So why this chromate ester rearrangement is happening? Because in case of allylic ester, if there is a scarcity of a proton just to get eliminated and form a ketone, in that case it will undergoes this type of rearrangement, forming this rearranged ketone. Now suppose you instead of this you have given this type of substrate. Instead of this was given, and they have told to consider the same reaction condition as above. What will happen? Just think, what will happen? This is totally similar, just there is a CH3 at the beta position of the double bond. So what will happen? So in that case there will be no reaction. In that case there will be no reaction. Because why? After this step it can go to this one, but you see there should be at least one proton to be abstracted to get this oxidized product. But in this case there is no proton available to be abstracted to get this oxidized product, and here is also no proton available to get this oxidized product. This will not give any oxidized product. Okay. Next topic we will discuss about, that is bi-releaser oxidation. So the bi-releaser, I am just discussing about this name reaction because in your assignments you will come to know about, you will just get these name reactions again and again and again. So if you get a clear idea whatever name reaction give which product, or how we can distinguish between two name reactions, both are oxidation but both are going through a same type of reagent, but if one name reaction will give one product but another will give a different product, but just by seeing the product you can get an idea which name reaction can perform. So that's why here I have almost included 7 name reaction which has been discussed in the last 2 assignments. So it will give you an idea, whichever has not been included in your classes or something, but you are listening getting those name reactions for the first time, that will give or whichever has been discussed also, to get a broader idea about those name reactions. I am just trying to discuss all this. The next is bi-releaser oxidation. The bi-releaser oxidation is an organic reaction that forms an ester from ketone and or lactone from a cyclic ketone using peroxy acid or peroxide as the oxidant. So this reaction was named after Bayer and Villiger. There are some limitations. So you can see, if we take a ketone and added peroxy acid or peroxide, what will happen? So undergoes a bi-releaser oxidation, forming O incorporation into this carbon-carbon bond and forming a ester. Whereas if you take a cyclic ketone, there will be also a O incorporation forming this lactone. Cyclic esters are called lactones. Cyclic esters are called lactones and cyclic amide are called lactam. When there is NH, it will be lactam. So if there is any mention as lactam, you don't know what is lactam actually. Lactam means cyclic amide. And lactone means cyclic ketone. There is a limitation. If any compound, suppose a compound contains a ketone as well as a double bond, there is a high probability, and if the double bond is also electron rich, there is a high probability that double bond get oxidized and give epoxide instead of oxidation of those carbonyl compound. Oxidation of the carbonyl compound. There is a high chance, if there is a double bond, electron rich double bond is available, there is a high chance of getting a epoxide product. What is the mechanism of this reaction? You can see first is if a peroxide is added, this oxygen will take a proton from this peroxide, forming this intermediate, then this will attack, opening up this carbonyl compound and forming this intermediate. After that this undergo a rearrangement where this OH comes here and this R1 from this carbonyl R1 here you can see that R dash has been shifted to the oxygen atom and these parts get removed from the system. So and you are getting this as your product with the acid as your byproduct. And so from here you can see mechanism, there is a shifting is happening. So there is a shifting of the alkyl group from the carbonyl center to this oxygen atom is happening. For this shifting, there is a requirement of anti-periplanar arrangement. There is a requirement of oxygen anti-periplanar arrangement of between this oxygen-oxygen bond. That means this bond, and in the peroxide the group that migrates here. They haven't here actually this group should migrate. They haven't drawn this one properly. Here you can see the anti-periplanar arrangement is between this bond and this bond. So just consider this one as a R prime and this as R. Then what will happen? This bond will be shifted. There is an issue in the picture. Okay, so this bond which is anti-periplanar with the oxygen-oxygen bond, that group will be shifted from carbon center to the oxygen center. I will discuss about some question and then I will discuss about some examples in the coming slides. First, just for here you can see that if this is R dash and this is R, these two bonds are anti-periplanar to each other, so this will migrate here and that eliminates. Okay, so those two bonds, this migrating bond and the breaking bond, the bond which is getting broken and the migrating bond, that should be anti-periplanar. What is anti-periplanar? Means they should be just opposite to each other. This is called anti-periplanar arrangement. If two bonds are opposite to each other with respect to another bond, there should be one bond in the between and the two bonds. This is called anti-periplanar arrangement. This is called anti-periplanar arrangement. So next we will discuss some examples of reductions. The question related to these oxidations we will discuss after discussing about this some three types of reductions. After that we will solve some previous year question and some question from books so that you will get an idea about this concept. So reductions, whatever we will discuss about Lütze reduction, Bartsch reduction and Clemmensen reduction. So what is Lütze reduction? So it is a selective organic reduction of alpha-beta unsaturated ketone to allylate alcohol. The reactive reductant is described as sodium borohydride, which is generated in situ from selenium chloride and NaBH4. So you can see if you are taking alpha-beta unsaturated ketone in presence of this reagent, this alpha-beta unsaturated ketone get reduced selectively. There is no reduction of this double bond. Normally, we have read about different type of reaction previously also. That those I am not discussing because we know those reaction for a very long time, like LiLH4, NaBH4. Okay, so here in case of LiLH4, if you add LiLH4 into this, what will happen? If you add LiLH4, what will happen? As this is a very strong reducing agent, it will reduce both the alcohol as well as the double bond. It will reduce both the alcohol and as well as the double bond. If you add only NaBH4, what will happen? In that case, as NaBH4 is a weak reducing agent, and due to conjugation with this double bond, this is also a very weak electrophilic center. This is a very weak electrophilic center. It is reluctant to react with a weak reducing agent. It is quite reluctant to react with a weak reducing agent. Therefore, we will not get any reduced product in case of simple NaBH4. We will not get any reduced product in case of simple NaBH4. Whereas if you add cerium chloride along with this NaBH4, we can get our desired reduced product. So you are understanding that problem and what we are overcoming by this reaction. Normally, if we add normal LiLH4, it can reduce the double bond also. We want to keep the double bond intact, so that if you add this one N2H4, in that case it will selectively reduce the double bond only. Selectively reduce the double bond only. Okay. So advantage, the Luce reduction can be conducted chemo-selectively towards ketone in presence of aldehyde, and moreover, if there is a system like this. And you are adding same the Luce reduction reagent, what will happen? It will selectively reduce the ketone. It will selectively reduce, whereas if you add any reducing agent, that will first reduce the aldehyde, then ketone. But in this case, just one step you will get the reduced product of the ketone. Okay, this is the advantages. The chemoselectivity of this reaction is the advantage of this reaction. So in presence of aldehyde, if you want to reduce any ketone, what reaction we will apply? We will apply this Luce reduction. So what is the mechanism? You can see the cerium chloride and NaBH4 forms this complex in situ, which react with the alpha beta unsaturated carbonyl center. Due to coordination with this one, it gains some electrophilicity. Because of that, this H- will attack here and forming this reduced product. Now in this case, what will happen? They have added cerium chloride, NaBH4, methanol. Along in the second step, they are adding HCl. What will be the product? I just give 2 seconds, just try. 5 seconds, sorry. So what will happen? In this case, there is alpha beta unsaturated ketone. So Luce reduction is selective towards the alpha beta unsaturated ketone carbonyl. So it will just reduce it and forming OH. So what will happen if you are adding HCl? This get protonated and get eliminated from the system, so minus H2O. or escape protonated and get element forming this carbocation. You know, formation of a 5-member ring are always stable rather than forming a 7-member ring. So instead of attacking to this place, it will attack this center, not this one, because the formation of 5-member rings are always stable. So this will get shifted. Now got the idea, if you have given to form a product from this one to this one, like you have given the retrosynthesis of this one to this. So what will reaction will perform? It will do first a Duche reduction followed by a acidification, then elimination. Next reduction type we will discuss, that is Barge reduction. This is one of the famous reduction. Barge reduction is an organic reaction that is used to convert arenes to 1,4-dicyclohexadiene. The reduction is named after Professor Barge. The advantage of this reaction is, you can see this phenol, simple phenol can be reduced to form this cyclohexadiene. The organic reduction of a aromatic ring. Aromatic rings are highly stable. You know that they are very reluctant to react in any chemical condition, but by this process we can reduce aromatic ring. Barge reduction does not reduce aromatic ring all the way to cyclohexane, but it is still it can perform reduction to cyclohexadiene, but it can't reduce it completely to cyclohexane. It's not possible. So factors. Sorry, there is a slight mismatch in that it should be. Sorry. This should be discussed in IVS. So mechanism, what is the mechanism of this reaction? In this case, you can see first the electron will take up one place of this aromatic ring and breaking this pi-pi bond in a single electron pattern, and in this way we will get the cyclohexadiene. But there is, if a ring contains any electron withdrawing or any electron donating group, there is a variation in pattern of electron addition to the electron abstraction from the ring in a different pattern. How you can see? In case of electron donating group, the one electron is added in the ortho position with respect to the electron donating group, and in this way we get this cyclohexadiene, where the double bond is conjugated with the directly conjugated with the electron donating group. Whereas if there is electron withdrawing group, the pattern will be reversed and we will get a double bond which is not directly conjugated with the electron withdrawing group. One carbon in a one carbon gap we will get this cyclohexadiene. So there is a pattern. Whenever you will see a electron donating group, you can get an idea that how you should play place the reduced double bond, and if you have an electron withdrawing group, then the placement of the double bond after reduction will be different. So what will happen in this case? They have given this substrate with the ester. Ester is also kind of behaves like an electron withdrawing group due to presence of this carbonyl compound. So it can behave as electron withdrawing group. So from that I got the idea that how the reduction will happen and you get the double bond of the cyclohexadiene. They have also added this one in the system. So you have to include this one. So how it will perform under you. Just give it a try. So what will happen? Like similar to this one, like just similar to this one. Up to this, the condition, the product formation will be same. So you will get this. You just draw this intermediate. This one. After this, the intermediate will be same. Now what will happen? Now you are adding this electrophilic group. So between these both are carbon centers are equally electrophilic. So what will happen? This comes back. Instead of taking proton from the NH3, here you can see, instead of taking proton from this protonating, there is a protonation source is given, alcohol. So instead of taking proton from the alcohol, what will happen? Instead of taking proton from the alcohol, it will attack to this center, forming this as our product. Okay, so here just because an electrophilic source is given, so from this you can get an idea. If any electrophilic source is given, then instead of taking proton from the protonating so alcohol or amine, it will attack to the electrophile, giving this substituted product. Next reduction we discuss about, that is Clemenson reduction. So what is Clemenson reduction? This is a chemical reaction described as a reduction of ketones or aldehyde to alkane. So it will just totally reduce the carbonyl center of the aldehyde or ketone to alkane using zinc amalgam and concentrated HCl. Advantage: so what is the mechanism of this reaction? The mechanism, when the zinc amalgam is added, this one electron is cancel. Further, then another zinc coordinates with this one, and to removal. This eliminates from the system. Then in a similar way, another zinc then when any HCl source is given, any HCl source is H plus source is given, both the zinc gets substituted with this H plus bonding. That's why you need a concentrated HCl, because you need a very high density of proton to substitute this to zinc from the system. So let's talk about some questions based on whatever we have discussed till now. So here two questions are given. So two retrosynthesis should be performed. So how can you get this two product from the respective substrate? From which method you will get this one? Just I will give 10 seconds. Let's give it a, we have just talked about Clemenson reduction. So in case of Luce reduction, what happens is the carbonyl gets reduced to alcohol. So there is no alcohol, so it can be performed. So this one is cut. In iodide reduction, that is also a reduction of double bond, that is cannot be performed. Barch reduction, that is also a reduction of aromatic ring or double bond or triple bond. That is also the correct option is the dimension reduction. In that case only the carbonyl group gets reduced to this alkane. Okay. Next one is this one. So in this one we have already discussed. You have to reduce the double bond selectively. So what will we have to perform? LiLH4, if we use LiLH4, what will happen? It will reduce both the ketone and the double bond. That cannot be performed. In NaBH4 mutual reduction, which this will just reduce this part. So the both get reduced, both double bond and ketone. In case of this one, only ketone get reduced. This is Barch reduction that can be applied for aromatic ring only. This is not aromatic ring, so the correct option will be this one. So the correct option will be this one. Okay. Next is this one. They have given 3 steps process, and in that after 3 steps we will get one product. Which product will you get among these 4? Just try. You have to try this by yourself, because otherwise you can't get an idea, because whenever there is a single step transformation you can predict what can be the product, but for the multi-steps transformation the product formation is, if you can't draw it the product after every step, there is a chances of mistakes. Let's start. So whenever divalage is added to this one, divalage reduce undergoes a one-step reduction, so it will reduce ester center to aldehyde. So this reaction, how this goes, divalage gives a H minus source, so that H minus will react to this center. Okay. So after that they have added this Grignard reagent, so the Grignard will attack to this carbonyl center. Now they have added PCC. So what will happen? You can see there is no selective oxidized product. There is no product where only this ketone get oxidized. So from that you can get an idea that in this case both the alcohol will be oxidized. So in this case the other 3 are not matching with this, so both will be oxidized. So our desired product will be option A. If there is any option where the ketone get oxidized selectively, that is possible, because in between allylic alcohol and ketone, secondary alcohol are, but in presence of PCC the allylic alcohol can also react, so that's why both of them will be oxidized to corresponding ketone. Okay. Let's go to our next question. So what is happening here? If you add sodium and ammonia, this is undergoes a Bart's reduction. The aromatic ring undergoes a Bart's reduction followed by MCPBA. That means benzoic acid. That means it will be undergoing a Baeyer-Villiger oxidation. So there is a combination of Bart's reduction followed by a Baeyer-Villiger oxidation. So if you don't know any of at least one of them, then you can't answer this question. So you have to know almost every important name reaction to attend any single question, because whatever question I am discussing here, most of them are from whichever came in previous year CSI, NET or GATE. So from that you can get an idea that this type of question can come in your coming examinations, whatever you are attempting for. So you have to know about the important name reactions. If you don't know whatever is happening or then just by knowing one or two you can't attend a question, because whenever there is a better marks question, there is a combination of two name reactions always. You won't be given a single name reaction for 2 marks. Okay, so let's start. So what will happen in this case? If you add sodium and ammonia, it will undergo a Bart's reduction. Now this OMe is a electron donating group. Now this OMe is an electron donating group. So in presence of electron donating group, the reduction procedure I have already discussed. So it should be conjugated to the OMe. So the option should be between option A or option B or C. Okay. This is already cut because here the OMe, the double bond, is not conjugated with the electron donating group. So D is already out from the options. Now in case of MCPBA, we know that whenever there is an electron donating group, that double bond get epoxidized. Whenever there is an electron donating group beside a double bond, that double bond selectively get epoxidized in presence of MCPBA. So you can see here between these two double bonds, which one is electron donating or electron rich? This one. Between these two double bonds, which one is electron rich? This one. And between these two double bonds, which one is electron rich? This one. So in this case, you can see so here the electron deficient double bond get epoxidized. Now see, this is correct. So the correct, so this should be, there will be two options actually. So which one is the correct one? Because see, both the product are no, actually this one is not possible, because here you can see this. If you draw the double bond like this way, this double bond is conjugated with the electron donating group, but this one is not conjugated with the electron donating group. So here is a trick also. So this is also not correct. This is also not correct. Both the double bond should be conjugated with the electron donating group. That process will be favorable, because here it is only one is conjugated, another is not. So between these two, this one is more favorable. So this one, and the after that the electron each double bond get epoxidized. So the correct option will be option B. Okay. So whenever there is a chance of conjugating a double bond with that electron donating group, wherever there is a greater number of double bond can be conjugated with the electron donating group, that pathway will be favorable. I am not drawing the mechanism, but you know that I have discussed in the earlier slides also. The electron will capture from one electron from the ring and will get this intermediate. Okay, let's go to our next question. So how will you get this product from this diol? From this diol, how can you get this product? So for pinacolon rearrangement, diol can participate in pinacolon rearrangement, but by that, by pinacolon rearrangement, you form a new carbon-carbon bond. But there is no formation of new carbon-carbon bond in this one from here to here. So this is not applicable. Next is Jones oxidation. So by Jones oxidation, here both are 1 degree in nature. Both are 1 degree in nature. And we know in case of Jones oxidation, what happens? 1 degree alcohol oxidized to acid directly. So but both of them are aldehyde, so this is also not applicable. In case of Baeyer-Villiger oxidation, only double bond. There will be a oxygen incorporation between the carbon-carbon bond, so there is no such oxygen incorporation. Also there can be a epoxidation of the double bond, so there is no epoxidation also. So that is also not applicable. So this is also cut. So the remaining is Swan oxidation. We know that in case of Swan oxidation, primary alcohol can be oxidized to aldehyde, just to aldehyde. So the correct option will be option C. Why not Jones oxidation? Because in case of Jones oxidation, the primary alcohol undergoes oxidize to form acid. Okay, so we will just choose the oxidation process where it can be oxidized just to aldehyde. So as that can be performed in various oxidizing reagent, but between these four options only Swan oxidation can perform this one. So that's why in this case, which one will be our correct option? Swan oxidation, option C. Let's go to our next question. So what they are saying, the major compound X formed in the following reaction exhibited a strong absorption at nu max 1765 cm inverse in the IR spectrum. The structure of the X is. So they are given a diol and adding PCC as the reagent, and we have told to predict what will be the IR spectrum, what will be the product. Now from the IR spectrum, you know this value we get for a ester. From if you will discuss about the IR spectrum, we haven't, because we haven't including the spectroscopy here. But if you go through the spectroscopy IR spectrum, from that value you can get an idea that this value comes for a ester. So your product should contain a ester center. The product should contain an ester center. So what will happen? So first, due to presence of this PCC and BCM, you know this one is primary, this one is secondary. So which is more susceptible to get oxidized? Obviously the primary one, because its reactivity is higher because of the high electron. This undergoes oxidation, forming this aldehyde. Now as its intermolecular nucleophile is present, so that here Now in medium there is already some PCC is there, so this further it will oxidize this one to form this ketone. So the correct option will be option D, and this contains a ester, so it also satisfying this concept that because none of them contain any ester group, only this one is containing a ester group. Okay, so for whenever you are seeing this value of iron, from that you can get an idea that there should be a ester moiety. We asked for the product of this reaction. So this is Birch reduction reagent. So what will happen? In case of Birch reduction, the aromatic ring can reduce, and also the triple bond can get also reduced. So that's why, and is electron withdrawing group, so that should be conjugated. And for Birch reduction, if a triple bond get reduced, the reduction, the product should be always trans. The product should be always a trans double bond. We will discuss that in the next class. The product should be always, in case of Birch reduction, the product should be always the trans double bond. We will discuss some examples in the next class also. I have forgotten to include this one. But in case of Birch reduction, from triple bond, if you are getting a double bond, that will be always a trans double bond. That should be always a trans double bond. If you see the mechanism, you can get an idea how this goes. Why not cis, always trans? So always a trans double bond. I will just try to get suppose this triple bond is given. Okay, suppose this triple bond is given. Now we add sodium, giving 1 electron to 1 carbon, and this is open now. So there will be a radical and there will be a negative center. Okay, now it will take another electron from the sodium and form this. There is a negative center, there is also a negative. Now if both are in the same side, there will be a huge repulsion between these two, so they should be placed opposite to each other. Because of that, we always get a trans double bond. So, and in case of aromatic ring, that double bond, the newly generated double bond should not be conjugated with that electron withdrawing group. So the correct option according to the aromatic ring between these two, and as this is contain only the cis double bond and this contains the trans double bond, the correct option will be this one. You have got this right? Why trans double bond always? Because if you just draw it like this way, negative charge means only the electron cloud, right? So there will be huge repulsion. There will be huge repulsion between them. Okay. So these two I am giving as a homework. Just give it a try. If not, we will discuss that in next class. From there you can get an idea, and I will try to discuss some more important name reactions. I have made the list, so from there we will discuss all these name reactions in the next 2-3 classes. Okay, we will discuss all the name reaction. Today we have discussed these three the others are remaining. So in the next upcoming classes, we will try to discuss all these name reactions. Okay. So I hope those will help you a lot. Thank you everyone. So this much for today's class. I'll just give an overview. So we have discussed different type of oxidation reactions, Orekin followed by this mechanism, Swan oxidation, this mechanism, Jones, PCC, Barr-Villiger oxidation, this mechanism, Lucci reduction, Barge oxidation, and also these two problems are remaining. Okay, let's try to solve these two. In case of Barr-Villiger oxidation, we know there will be oxygen incorporation, but the migration property, if suppose both of these, between these both carbon-carbon, which will be migrated? Now the migratory ability is always tertiary greater than secondary greater than aryl then primary. So between these two, this carbon is tertiary. So this is secondary. This one is primary. So which will have greater migratory aptitude? This carbon. So the product will be the product will be this one. Now from this question you have got an idea that which, if this is tertiary, that will migrate faster than secondary, then aryl, then followed by last is primary. Now try to solve this one. I just give 1 minute. This is the last question for today. So now see, this one carbonyl group, this carbon is 1 degree, whereas this carbon is 3 degree. So which will migrate? Obviously this one. So the product will be just, rest of the system will be intact, only there will be oxygen incorporation between this carbon-carbon bond. The rest will be intact. I am not drawing the rest. Okay, understood? Now we know about Barr-Villiger oxidation. So if any question comes based on this concept, you will be able to attend that. Okay. Thank you everyone. Thank you. We'll meet in the next class, same time, 4 p.m. Have a nice day.